So when we left off with membrane transport, we were talking about gradients, and we specifically were talking about chemical gradients to understand the first component of something that we're going to see a lot in this course called the electrochemical driving force. So right now, we are drawing a cell where we have a chemical driving force that points outward. Now, in order to leave these captions on, I'm going to draw at the bottom of this slide here with the annotation tool instead of switching my camera because I'm not sure they'll get picked up anymore. Okay, so when we're talking about our, oh gosh, we're at meeting tools. Okay. When we're talking about a chemical driving force, in this case, we're looking for one going outward. So we start with our cell. We have our extracellular fluid. We have our intracellular fluid. And we're going to have solutes. So the solutes are what we're tracking when we're talking about our chemical driving force, our CDF. Okay. So if we're looking for a force going outward, we know that our chemical driving force just responds to the chemical gradient, and that molecules are going to move from an area of high concentration to low concentration. So if we're looking for a force going out, we'll have lots of solutes inside the cell to produce that high concentration. And then we'll have a lower number, so just a few outside. So this will produce an outward chemical driving force. Now, the trickier part of this question was really the second part, to come up with some scenarios where we would not have our solutes following this gradient. So why would we not have something flowing from the inside of the cell to the outside of the cell when we have a chemical gradient that should be pushing them outward? Does anyone want to volunteer a couple of reasons they think this might happen?
Would it be possibly because the molecule is too large to pass through the phospholipid bilayer?
Absolutely. So if our membrane isn't permeable to that solute, whether it's too large or whether it has to do with a charge, if we can't get that solute, we can't get that molecule across the membrane, we won't have movement no matter what our gradient looks like. Okay. Anybody come up with a different reason? I could think of 3 reasons. Yep, you could go again.
There's not enough ATP to facilitate transport?
So we'll get to active and passive transport in a second. So you're right to be thinking on the line of transport. In this case, we actually don't need ATP in order to allow these solutes to follow the chemical gradient because they could passively flow down the gradient. However, if we have ATP being used to transport something against this gradient, then we wouldn't see this flow of molecules. So if we have active transport happening, we might not see this type of movement. Then the last reason, I'll just give you because we're about to talk about it, but the last reason we might not see something following its chemical gradient, following the chemical driving force, is if we have an opposing electrical driving force. So when we're thinking about the movement of solutes, and specifically when we're thinking about the movements of ions, which have charges, we also have to factor in the electrical force on that solute. We can't think about just the chemical gradient. Okay, so we're going to add into our picture of the movement of solutes that electrical driving force now. Okay, so we went over some brief terminology on Wednesday. So we talked about how ions are charged particles. They can be either positively charged or negatively charged. So we have cations and anions. When we're measuring the electrical driving force, one of the numbers we're going to need to know is the membrane potential. So the membrane potential is a force caused by the unequal distribution of anions and cations across the cell membrane. So when we have a charge separation, when we don't have equivalent charges on either side of the membrane, we're going to have a membrane potential that's not zero. There will be some way we can measure this difference in electricity, basically. So we measure it in millivolts. And we always want to reference the intracellular fluid. So we're going to have a polarity in addition to just a number. So we're going to have both magnitude and polarity. So we'll see numbers that are negative and sometimes numbers that are positive. Okay. The principles we need to understand the electrical driving force are first that we're going to have opposite charges attracting. So positive charges are attracted to negative charges and vice versa. Like charges repel. So negatively charged ion is going to move away, be repelled by a negatively charged area. The direction of our electrical driving force is therefore going to depend on two factors. The first is the polarity of the cell. That's because we need to figure out whether the inside of that cell is negative or positive. At rest, cells are usually negative, but when they're excited, they often turn positive, and we'll see that in the case of neurons. So we'll look at what that does in a cell. So we want to know whether that cell is positive or negative. And then we also have to look at the charge on the particle. So when we're looking at the electrical driving force, we need to really pay attention to what ion we're tracking, what particle we're tracking. And that's because whether that particle is a cation, so whether it's positive or whether it's negative, that's going to change how it interacts with the polarity of the cell. So we can't just have a general electrical driving force. It's going to be on a specific type of ion, a specific charge. So this is a picture of how we could create this membrane potential, how we create a separation in charges. So here we see the intracellular fluid on the left, the extracellular fluid on the right. We see a plasma membrane between them. And the part about that plasma membrane is important because the plasma membrane separates these two fluids, and charged particles cannot cross this membrane without specific transporters. They might need channels, they might need active transport. They're going to need to go through an integral membrane protein in order to cross. So the plasma membrane can create a separation in charges. So they won't reach equilibrium if they can't go across. So we have, in this case, excess anions, or negatively charged ions, negatively charged particles inside the cell, creating a negative charge. We have excess cations, or positively charged ions, on the outside of the cell in the extracellular fluid, creating a positive charge. So this is what it would look like if we're drawing that membrane potential, if we're drawing this separation in charges. And we want to track the direction of the force. So we need to know the polarity of the cell, and we need to know the charge on the particle. So here we have two simplified drawings. So in figure A here, this is showing us a negative membrane potential. So it's showing us negatively charged particles inside, positively charged particles outside. Although in reality, like in that previous picture, we'd have a mix of positive, negative in both places, but we're tracking here the excess charge. Okay, so excess of negative on the inside, excess of positive on the outside. And here we see a positively charged particle, so cation. The electrical driving force for that cation will be into the cell, and that's for two reasons. The first This positive is attracted to negative. So this particle is going to want to move towards those negative charges. And the other is that these positive charges in the extracellular fluid are simultaneously repelling this positively charged cation. So it's being repelled by the extracellular fluid, so that also has the effect of pushing the cation in. So it's both being pulled by the inside of the cell and pushed by this extracellular fluid, by this positive charge outside the cell. We see the reverse happening if we're tracking an anion, a negatively charged particle. So here we're actually still looking at that same cell. So negatively charged on the inside compared to positively charged on the outside. But now we're tracking this negative particle. And here we're looking at this negative particle on the inside. So we can see that we have a negative charge along with all these other negative charges. It doesn't want to stick around. It's being repelled by those negative charges, attracted by the positive charges outside. So the electrical driving force is going to push towards the outside of the cell. Now these anions and cations are only going to be able to move if there is a protein in that membrane allowing them to move. In this case, in this unit, we're mainly going to be tracking the forces themselves. But when we start talking about neurons especially, we're going to have to pay careful attention to whether the particles, whether the ions are actually able to cross the membrane. Because sometimes they will want to, but won't be able to. Okay. The electrical driving force also has a magnitude. So what we were just talking about was the direction of the electrical driving force, but it's also basically going to have a size. The size of that force, the magnitude of that force, depends on two things. The first is the strength of the membrane potential, which is basically how negative is that inside, how big is our charge separation. So not just what type of charge, what polarity does this cell have, but also how much of a charge does it have. We also have a characteristic of the ion itself that has an effect on the magnitude. So the magnitude of the force also depends on the amount of charge on our ion. So usually we see things like Na+, right, a sodium ion that just has one positive charge accumulated there, but we'll also see that calcium ions are Ca2+, so they have basically double the charge on them. So we'll see a greater magnitude for the electrical driving force on ions like that, with a greater charge on the ion itself. So in these three figures here, or these three subparts of the figure, the arrow, the size of the arrow, the width of that arrow is expressing how big the electrical driving force is on that particle. So what we're paying attention to first is the strength of the membrane potential, so expressed as Vm. We can see that it's -50 millivolts in figure A. We can see it's negative on the inside, positive on the outside. That's what Vm equals -50 millivolts means. And we're tracking a cation, so positive ion, on the outside in the extracellular fluid. That negative membrane potential is going to pull on that positive charge, pulling it towards the cell, pulling it towards the inside of the cell. But we can change the magnitude of that electrical driving force. We can make it pull harder if we change the membrane potential. So if the inside of the cell becomes more negative, we have a greater separation of charges. So the inside is more negative compared to a more positively charged outside. We get to say -100 millivolts on the inside. That same cation, so that same cation with the same amount of charge on it, is going to get pulled harder because that charge is more negative on the inside. So if we have a greater magnitude of the membrane potential, so a greater value here, 100 versus 50, it's pulling harder on that particle. The second way we could get a higher electrical driving force, so compare figure C to figure A here. So we can see that we have the membrane potential back down to negative 50 millivolts. So we're back to that original resting potential. But we have a bigger arrow, we have a greater magnitude of the electrical driving force because the particle we're tracking has more charge. So here we see 2 plus signs on that ion, on that particle. And so we have a greater electrical driving force, even though our membrane potential is the same. Questions about the electrical driving force before we sum it together with the chemical driving force? Okay. So when we're looking at the electrochemical driving force, we're looking at the total force on a particle. So we can track its chemical gradient, and we can track the electrical driving force. But to figure out which direction that particle is actually going to want to move, we need to look at both. So we're going to sum together the chemical and electrical forces on any given particle. Now, we have to be a little careful here because when we're looking at a specific particle, so in this case, potassium, we have to make sure we know what factors are going to influence the chemical driving force and the electrical driving force. So when we're looking at the chemical driving force, in this case, we would be looking at the concentration of just potassium. So potassium inside the cell versus potassium outside the cell. So for the chemical driving force, the amount of, say, sodium ions would make no difference to us. So the chemical driving force would just be the potassium gradient. For the electrical driving force, however, we're just looking for the charge. So when we calculate the electrical driving force, it is going to make a difference if we were to, say, have a bunch of sodium ions out here in the extracellular fluid. Sodium ions also have a positive charge. So they have an effect on this electrical driving force for potassium, even though it's a different ion. So when we're looking at the chemical driving force, we're looking at just that ion. When we're looking at the electrical driving force, we're looking at any charged particle. Okay. So that's important to know as we start to add these together, that we need to keep in mind whether we're tracking just the one particle or whether we're tracking many different species of ion. Our end goal for this is to figure out what direction the total force is. So what direction any given individual particle is going to want to move. So we're going to compare the chemical and the electrical forces because they basically sum together. Okay? So we're going to add them together and we're going to come up with a direction. Now, if the chemical and electrical forces are acting in the same direction, that's our easiest case, really. If both the electrical driving force and the chemical driving force are pushing our ion out of the cell, then our ion is going to want to move out of the cell. The magnitude of that electrochemical driving force would be the chemical force plus the electrical force. So the electrochemical driving force in this case would be stronger than either the chemical driving force or the electrical driving force individually, but it would have the same direction as each. All three forces would be pointing in the same direction. Now it gets trickier when we're thinking about chemical and electrical forces that are acting in opposite directions. So if we have a chemical driving force pushing our ion out of the cell, but an electrical driving force pushing that ion into the cell, then we end up with a conflict. Fundamentally, the electrochemical driving force is just going to act in the direction of the stronger force. So if we have a greater magnitude of the chemical driving force, that chemical gradient is really strong, we have a really high concentration of that ion somewhere, then the electrochemical gradient would follow the chemical driving force. But if we only have a small chemical gradient and we have a lot of electrical forces acting on that ion, we have a really big buildup of charge somewhere, then the electrochemical driving force will follow the electrical driving force. So we need to compare the magnitude of our forces. So our magnitude will be the larger force minus the smaller force. Okay. So we'll have a slightly smaller electrochemical driving force than the dominant force overall, because we have something opposing it, we have something pushing against it. Okay. This is similar to the question I asked you at the beginning. So if we have a chemical gradient that exists, under which conditions would a particle not be transported, even if the membrane is permeable to that particle? Kind of answered this at the beginning, but now that we've talked about the electrochemical driving force, we know that the answer is that when the electrical force is opposing that chemical force, we are going to not have movement across the membrane. So if we have a chemical gradient pushing our ion out, but we have an electrical force pushing that ion in, we're not going to have movement of that particle. So this state where we have no movement of our ion, despite the fact that we have both a chemical driving force and an electrical driving force, is called our equilibrium potential. So the equilibrium potential is a type of membrane potential. And specifically, it's a value that tells us when the chemical driving force is completely equivalent to the electrical driving force. So if the chemical driving force exactly opposes the electrical driving force, we're at the equilibrium potential. Now, it's important to note about the equilibrium potential, which is abbreviated E with then a little sub letter here, that when we're looking at the equilibrium potential, we're going to have an equilibrium potential for a specific ion. Now, can someone tell me why we don't have just a general equilibrium potential for everything in the cell? Why are we tracking here the equilibrium potential for potassium specifically?
Is it that the electrical force for individual particles vary and the driving force would change per particle?
Yeah, the driving force changes per particle. You mentioned the electrical driving force. That's true because we have to take into account the charge on the particle. But it's specifically for potassium in this case rather than any positively charged particle, because the chemical driving force is dependent only on the potassium gradient here. So we need to look at the equilibrium potential for potassium specifically, because what this equilibrium potential is telling us is when the chemical driving force exactly opposes the electrical driving force. Okay. So one component of this is dependent only on that individual ion. So in this case, it's showing us a chemical driving force equivalently opposing our electrical driving force. And it's telling us that the equilibrium potential for potassium here is negative 94 millivolts. So what that's saying is when the membrane potential, so when the charge separation on this cell, when we have negative 94 as our charge inside the cell, that is when the electrical driving force is big enough to oppose the chemical driving force on potassium here. Okay. So this is dependent slightly on environment. And as we can see, it's telling us a membrane potential. It's telling us the value of the membrane potential we need in order to pull hard enough to oppose this chemical driving force. Okay. So when we're at our equilibrium potential, so when the membrane potential is equivalent to our equilibrium potential for that ion, we'll have a force of 0 because these forces, the electrical driving force and the chemical driving force, are in exact opposition. So there would be no net force here. So even though we have an equilibrium potential, right, we have a number there, it's -94. That is our membrane potential, -94, so we're at rest. So there's a number here, but if I were to ask you for what the force was, what the electrochemical driving force was, that's different. We're summing our charges, or sorry, we're summing our two driving forces because they're in opposite directions. The value for that electrochemical driving force would be 0. Okay. Unfortunately, we're not always going to have equilibrium across our membranes. We're not going to always be at this equal opposition of forces. Actually, I guess fortunately, because otherwise your body would not work. Okay. So what we want to be able to tell as well is what direction our forces are going to be pushing. If we look at the membrane potential, so the charge separation that exists across our membrane, compared to the equilibrium potential, so that point at which the two forces will be equal. Now this takes some sort of mental thinking, so after class I do want you to sort of mull this over, and we'll also be reviewing this again later. I know we have 10 minutes left of class, but this is going to take a little while to internalize, or at least it did for me when I first learned it. Okay, so when we're looking at our equilibrium potential and comparing it to the membrane potential, so what the cell is actually at, we can see that often our membrane potential of the cell, so the actual charge separation, is not the same as our equilibrium potential. So when these two values, our membrane potential and our equilibrium potential for that ion, are not the same, it means we do have an electrochemical driving force. So there is a total force acting in some direction. And we can tell that because if there was no force, we would be at our equilibrium potential. So if there was 0 electrochemical driving force, our chemical driving force and our electrical driving force together would be 0. That defines our equilibrium potential. So as soon as we see a membrane potential that is not the equilibrium potential, we know we have an electrochemical driving force. Now, the electrochemical driving force is going to follow the stronger force. So when we see a membrane potential that is weaker than our equilibrium potential, what that means is our chemical driving force is, if we see a membrane potential that's weaker than the equilibrium potential, that means that our chemical driving force is stronger than our electrical driving force. Okay. So we'd have to reach -94 for these two forces to be equal. We're not there, and the reason for that is our chemical driving force. Now, the opposite is true if our membrane potential is stronger than our equilibrium potential. So in this case on the right, we see that the membrane potential is -100 millivolts, but our equilibrium potential is -94 millivolts. So what this means is that that electrical driving force is stronger than our chemical driving force. So we have an electrochemical driving force moving into the cell in this case. Okay. So this is telling us if our membrane potential stronger than the equilibrium potential, we have a larger electrical driving force. So these are the factors we want to look at when we're trying to figure out what the net force on any given particle is. Okay. So as we're moving forward, I think these questions are relatively easy, so we're not going to go into breakout groups for them, but you should make sure that you understand them. So at this point, we should be able to describe the difference between passive and active transport, although we're going to get into a lot more detail on that soon. You should be able to understand why a concentration gradient is referred to as a driving force. So why does a gradient become a force? We should be able to look at a table like this and determine which direction a chemical driving force would go. So that's a good problem to sort of try at home for you guys. So if we have a chemical driving force on amino acids, if we look at the value inside the cell, we look at the value outside the cell, which direction would that force go? So as you're studying for your exam and practicing for your exam, go ahead and try practicing with a couple of these different values of the ICF versus the ECF. Make sure we understand that force. Okay. We have a couple minutes. You know what? Sue is right. I am sorry that I didn't get these up for you earlier. We actually only have 5 minutes, so we're going to break 5 minutes early, and we'll start out with this on Monday. So we'll start with membrane transport part 2 on Monday. So you guys should be ready to go with your quizzes now. So go ahead and do those after you look over your notes a bit. And I'll see you again then.